Okay, so here's a video about minimum weight spanning trees and Kruskal's algorithm. This is from page 82 and 83. um, right, here's basically the problem. Say we're given a connected graph with edge weights. So down here I drew a picture. Here's a connected graph, and I drew some numbers by the edges, and these are considered the weight of the edge, whatever that means. And what we're looking for is I would like a spanning tree of the graph, and I would like the sum of all the edge weights in the tree to be as small as possible. So I drew a pretty easy example. This has some edges of weight 1 and then some edges of weight 100. And if I want to draw a spanning tree and I want the sum of the edge weights to be as small as possible, then maybe it would be a good idea to avoid these 100s. So maybe I'll draw this edge, which has a weight of 1, this edge that has a weight of 1, and then I still need to draw more because I need it to be a spanning tree. But I can draw this edge that has a weight of 1. And then it's a spanning tree. And this, it's not too hard to see that this is the smallest possible weight of a spanning tree. We have 4 vertices, so a tree on 4 vertices should have 3 edges. And out of the graph that I was given, there were 5 edges, and 2 of them were hundreds. So clearly it's going to be best possible if I just use the 3 that don't have weight 100. You know, if I use 100, then my total weight is going to be at least 100. That's going to be way more than this. So this is definitely the smallest the smallest weight spanning tree. Sometimes there's a tie for the smallest weight spanning tree, so as usual I'm going to try to be careful with my language. I might slip up a little bit, but I'm going to try to use the word a spanning tree rather than the, let me start again, a minimum weight spanning tree rather than the minimum weight spanning tree, because there may be several spanning trees that have a tie for the smallest possible weight. In this case, there's just one minimum weight spanning tree, actually. So, yeah, actually, on this other sheet, I wrote just a little bit more formally. We have a weight function. You know, in the picture, I just drew some numbers next to the edges, but more formally, we have a weight function, W, that goes from the edge set of a graph to the real numbers. And so you can talk about like W of E for a particular edge. And for a subgraph of G, we say that the weight of the subgraph is just the sum of the weights of the edges in the subgraph. So what we're really looking for in this problem is I would like to find a spanning tree T such that the weight of T is as small as possible. The W of T is as small as possible. And yeah, so before I get into this, let me just mention that this is a pretty real world problem. Like, you can imagine that we have some cities, and we would like to connect some of our cities with roads, but maybe it's very expensive, or maybe it's very difficult to build a road directly from one city to another. For example, maybe I have these 4 cities, and for some reason, maybe there's just a lot of mountains here or something, but for some reason it's very difficult to build a road directly from this city to this city, and that's why this has a weight of 100. Sometimes these weights are called costs. So you can think of this 100 as like it's very expensive or very difficult to build a road directly from here to here. And yet, I would definitely like to be able to get from this city to this city. So I want to have a connected graph. I want to have a spanning tree. A spanning tree is basically a set of edges that will allow you to get from every city to every other city, or every vertex to every other vertex. Um, but we don't want to use the expensive edges, or the heavy edges, the ones with a lot of weight. So that's how this is a real world problem. And so it has a simple solution. There's an algorithm to solve it. An algorithm is just, well, it's just a sequence of steps, the instructions that you can follow, and it's guaranteed to give you a minimum weight spanning tree. So let's say you're given a weighted graph. So you're given a graph and the edges have weights on them. I'm going to build my spanning tree one edge at a time. I'm going to start with no edges at all in my structure. I guess I shouldn't call it a tree yet, because a tree has to have n-1 edges on n vertices. So I start with no edges. And then at step I, I'm going to select an edge to go into my set of edges. And I'm going to select it to have the smallest weight out of all the edges in G that would not form a cycle with my previously chosen edges. So for my first edge, I'm just going to choose a smallest weight edge, because there's no way, because I don't have any edges yet, there's no danger that I'm going to choose an edge that would make a cycle with previously chosen edges, because on the first step, there are no previously chosen edges. But as I go on, I have to be careful not to choose an edge that would make a cycle with my previously chosen edges. And of course, that's because I'm building a spanning tree, and trees aren't supposed to have cycles. And we will prove this, but in the end, after you've chosen the right number of edges, and once again, there should be n, let me make this clear. We're given a graph G with n vertices. And yeah, as usual, I'm just using the letter n for the number of vertices, but I just wanted to make that clear. So the number of edges in a tree should be n-1. And what this is saying is, if you follow these instructions, by the time you get to the n-1th edge, you will have a tree that is a minimum weight spanning tree. So before I prove that, let me just show you this in action. So here we're given a slightly more complicated graph. Actually, hopefully it's clear enough. I know it's a bit jumbled in the middle, but so this edge has weight 4. This edge has weight 5. This edge has weight 3. This edge has weight 1. So I know it got a little bit jumbled in the middle, but hopefully it's clear enough. Okay. Let's go. So I start with this picture. It has no edges in it. I drew all 5 vertices because they all need to be there. This is going to be a spanning tree. And now at step I, I'm going to let the edge E sub I be, and I notice I could be a bit more careful with my language here. E sub I is going to be a smallest, because there might be a tie, a smallest weight edge that does not form a cycle with previous edges. So this is my first step, so there are no previous edges, so there's no danger that I'm going to make a cycle. So I'm just going to choose one of the smallest weight edges, and actually there is a tie. This edge has weight 1, this edge has weight 1, and 1 is the smallest. Why don't I go with this one? Okay. Now step 2. I'm going to choose a second edge, and it's going to be a smallest weight edge that I haven't already chosen yet, and it doesn't make a cycle with previous edges. Now, I only have one previous edge. There isn't really any danger that my second edge is going to make a cycle with my first edge. The shortest possible cycle has 3 edges, so there's no danger of having a cycle if I'm only going to put in my second edge right now. And so my second choice is just going to be the smallest, and actually now I realize that no matter what happened, I was going to choose both of these ones. So that's what happens. And now I keep going. Out of the rest of the edges, the ones that wouldn't form a cycle, and actually I would say there's still no danger of me forming a cycle. Even if I add this edge or this edge, that won't complete a cycle. So I'm looking here at the weights of edges, and I see some 2s. Either one of these 2s could go in. And if there's a tie, then you just make the decision however you like. So I'll put that 2 in. Okay. Now things have gotten slightly interesting, because now I have to go in and choose another edge. I guess I really just need one more edge, so it's lucky that things got interesting. Because I have 5 vertices, so I would need a total of 4 edges, and I already have 3 edges, so this is going to be my last edge. Now, so I go in here and I look around for the smallest possible weight of an edge that would not make a cycle. So I'm looking for low numbers here, and of course I'm not looking at edges that I already drew over here. So one thing that jumps out at me is this 2. But if I drew that, that would make a cycle. So this one is off limits. I'm going to have to choose a 3. Well, maybe. This edge has a weight of a 3, and that would be this. And I guess that wouldn't make a cycle. But before I go and draw it, let me just take a look at this 3. I would say this edge is also an option, because that would go here, and that would also not make a cycle. Maybe I'll choose that one just because I like my pictures not to have edges crossing. Like, there's nothing wrong with crossing edges. It's just visually frustrating. So I'll draw this 3. But I could have drawn either one. And what I'm telling you is that this spanning tree has a weight of, I guess, 7. And out of all the possible spanning trees of this graph, you might be able to find other spanning trees that also have a weight of 7, but you won't ever be able to do better than 7. Oops. Yeah, there we go. So 7 is the minimum weight. All right. So let me run through a proof of correctness for this algorithm, because I've told you the algorithm. The algorithm is just a sequence of steps for you to follow. But the claim is that this algorithm always produces a minimum weight spanning tree, meaning that whatever tree comes out in the end has the smallest possible weight of any spanning tree, and that takes some proof. So that's what we're proving. And this is going to be basically by contradiction. So suppose not, meaning suppose that the tree that is output by the algorithm is not a minimum weight spanning tree. And then what we're going to say is let H be something that actually is a minimum weight spanning tree. So in particular, the weight of H would be smaller than the weight of T, because we're saying that T is not a minimum weight spanning tree. In other words, something that is a minimum weight spanning tree should have smaller weight than T. So we choose H to be such a thing. In particular, we choose H so that out of all of the minimum weight spanning trees, and again, this is where it gets awkward because we have to consider the possibility that there's a tie. There might be a bunch of minimum weight spanning trees, and we're saying that out of all of them, H shares the largest possible number of edges with T. So H and T are different trees, but they may have edges in common. And we're saying that out of all of the possible minimum weight spanning trees, H shares the largest possible number of edges with T. And this is all part of our strategy to get a contradiction. Let E sub I, and remember that as we're running this algorithm, we have these edges, like the first edge we choose is called E1, and then E2, and then E3, and right under the description of the algorithm, we let E sub I be a smallest weight edge such that it does not form a cycle with previous edges. So that's what these E sub 1, E sub 2, E sub whatever are. And I'm going to let E sub I be the first one of those, so it's the smallest value of I, that is an edge of T and is not an edge of H. Because maybe they have several edges in common, once again. But they aren't the same tree. T and H can't be the same tree because H is a minimum weight spanning tree and T isn't. So there's definitely some edge in here that's not in there. And so we say let E sub I be the first one. Now, here's what we're going to do. We're going to consider another graph, H plus E sub I. This plus just means I'm putting in a new edge. I'm taking H, which is a tree, and then I'm putting in an additional edge that was not in H, right? Because E sub I, we said, was not in H. And of course, maybe I'll just use this page to doodle a bit. You know, what happens when you take a tree and then you put in an edge that wasn't in the tree? It makes a cycle. Like if what I had before was a tree and then I put in a new edge, and that makes a cycle. Why? It's because this is a tree, there was already a path from this vertex to this vertex, right? There was this path. And so when I draw this extra edge in there, that makes that path into a cycle. Like I can go all the way around now. So we just made G naught by taking a tree and then putting in an edge that wasn't in the tree. So that graph has a cycle. So that cycle can't be contained in T because T is a tree. We have two trees, H and T, but they're both trees, and so neither one of them has a cycle. So this cycle that's in the graph G naught, that cycle must have an edge that isn't part of the tree, because otherwise the whole cycle would be part of the tree. So C must have an edge E naught that is not present in T. Then I'm going to let T naught be the graph G naught after removing the edge E naught. So it's sort of like this. We started with a tree, then we put in an extra edge. Now that has a cycle. Now I'm going to find a different edge, possibly the same edge, but really any edge on this cycle, and remove it. And then what's left is also a tree. That's the trick. You can start with a tree, and then put in an extra edge, and that makes a cycle. And then you can remove any edge of that cycle and get a new tree. So that's what T naught is. T naught is a different spanning tree of G. And the weight of T naught, if you track our steps and remember what we did, we made T naught by taking H, which is a minimum weight spanning tree, and then putting in an edge to make G naught, and then taking out an edge, a different edge. So in other words, we started with H, and then we put in the edge E sub I, and then we removed the edge E naught. So the resulting weight should just be the weight of the graph that we started with, plus the weight of the edge that we put in, minus the weight of the edge we took out. And meanwhile, H is a minimum weight spanning tree, so we know that T naught is a spanning tree, and H is a minimum weight spanning tree, so the weight of H must be less than or equal to the weight of T naught. This is true of any spanning tree. The weight of H is less than or equal to the weight of any other spanning tree. And so I look at this inequality, and I can cancel the weight of H on both sides, and then I could move this over, and I would conclude that the weight of E sub I is greater than or equal to the weight of E naught. Okay. Now we're going to think about what the algorithm does. The algorithm at each step, it chooses the edge E sub I so that it doesn't make a cycle with the previously chosen edges. Basically, if I'm looking for what is a suitable choice for E sub I, it's something that I could put here such that this set of edges wouldn't have any cycles. And notice that I didn't write E sub I here. I wrote E sub naught here. And there's a reason for that. What I'm arguing is that E naught would have also been a suitable choice for E sub I. Because, what am I saying here? This set of edges does not have a cycle because this set of edges is all contained in, for example, this is contained in G naught, right? Because H and T both have all of these edges in common. E sub I is the first edge that they don't have in common, but H and T both have all of these edges in common. So H had all of this, and G naught also had this edge. G naught only had one cycle in it, and that was the cycle C, because when you take a tree and you draw one extra edge, that only makes one cycle. So there's only one cycle that could possibly be in here, but that cycle's not in here because the cycle C, the cycle C had the edge E sub I, but this does not have the edge E sub I. So this set of edges doesn't have a cycle, meaning that when I was doing Kruskal's algorithm and when I was on step I, remember when you're doing the algorithm, sometimes you have arbitrary choices to make. So sometimes you say, well, the next edge could be this one or this one, and so I'm just going to just going to pick one. It doesn't matter. So it's possible that step I was like that. It's possible that when we chose the edge E sub I, it's possible that there were other choices that we could have made. And that's basically what we're arguing must have happened. Because, okay, once again, the fact that this set of edges doesn't have a cycle means the following. When we got to step I, we were looking for any edge that I could put here and have it not make a cycle with the rest. And we know that E sub I was an option because E sub I was the option that we chose. But this is also saying that E sub naught was also an option at that point. And if we chose E sub I instead of E sub naught, that could only be because when we're looking for this edge, we choose the suitable edge that has the smallest possible weight. So if we chose E sub I instead of choosing E sub naught, which is what we did, then that could only be because E sub I has less than or equal to the weight. They might have been equal, in which case it's a tie, in which case our choice was arbitrary, or it could be strictly less than. But look at where we are now. We had from before that the weight of E sub I was greater than or equal to the weight of E naught. Now we have the other inequality, so that shows that they're equal. So actually it was a tie. When we got to step I, we could have chosen E sub I for our next edge, or we could have chosen E sub naught for our next edge. But so where does that put us? We go back to this other tree, T naught. Now that I know that this number equals this number, the weight of T naught is just equal to the weight of H. We know that H was a minimum weight spanning tree, so if T naught has the same weight as H, then that means T naught is a minimum weight spanning tree. And this is our contradiction because remember how we chose H. Out of all the minimum weight spanning trees, we chose H to be such that it shares the largest possible number of edges with T. And what we just did was we made a different spanning tree. Our different spanning tree is T naught. T naught is a minimum weight spanning tree. And it shares more edges with the original tree T than H does. Why is that? Because, well, look at how we got T naught. I took H, I put in an edge that is in T, because E sub I is in T. So I took H, and then I put in an edge that is in T, and then I removed an edge that is not in T. So the resulting graph shares one additional edge with T, right? So once again, T naught has the same weight as H. It is also a minimum weight spanning tree, and yet it shares more edges with T than H does, and that's a contradiction. So therefore, T is the minimum weight spanning tree. Or, well, I slipped up. A minimum weight spanning tree. All right.